about parallelograms today. So yesterday we talked about trapezoids and isosceles trapezoids. The day before we talked about kites and rhombuses. Now we still have parallelograms, and then everything that we've talked about today and yesterday is going to apply to a rectangle and a square, and then throw in the stuff from Tuesday as well, and we get the square. So everything we've talked about gets the square. Everything from the last 2 days goes to a rectangle, and then we're going to add on the stuff from today as well. Okay? But let's go ahead and get started by talking about some properties of a parallelogram. First of all, what is the definition of a parallelogram? It's not going to be in your notes, but, well, it'll be in your notes from before. It's not in your notes from today. So I have to have two sets of parallel lines. When I have those two sets of parallel lines, there's certain properties that show up that I can look for and actually use to define a parallelogram. We'll get to those later. Let's talk about those properties I have first. First one is that my opposite sides are congruent. And this comes back to if I have two parallel lines, the distance between those lines is always going to stay the same, no matter where I'm at along those parallel lines. And so it's impossible to connect them and have those lines still be parallel and be a different distance. Okay, so that one's one we kind of just got to think about, but it should start to make sense because that distance between our parallel lines is always the same. Okay. Next one, we have that opposite angles are congruent. So the angles across the figure are going to be congruent. We're actually going to prove this one here in a second. Okay, so those opposite angles are going to be congruent. Next, we have that the diagonals intersect at their midpoints. So if I have diagonals that are intersecting at their midpoints, what's another way to phrase that? They're bisectors, right? They bisect each other. Okay, so if they're intersecting at those midpoints, they're bisecting each other. Did I say that they're bisecting at a perpendicular angle?
No.
No. Okay, we're actually going to find that that hardly ever happens unless I'm in a rhombus.
Or
Okay?
square.
Or a square or a kite. But as far as a parallelogram, that's not going to happen too frequently. All right. I think this is our last one. We have consecutive angles are supplementary. All right, so consecutive angles are supplementary. That's one we talked about yesterday. That applies to a trapezoid. So this is actually not a new property. This comes from a parallelogram is a trapezoid. So this one has to apply to it as well. So I have the opposite angles are congruent, and then the ones next to each other are going to be complementary. Or supplementary, sorry. All right. One thing we've talked about with all of our shapes so far is symmetry. Does a parallelogram have symmetry?
Sometimes.
No.
I heard sometimes, yes, no. Let's look. If I try and draw a parallelogram here. Okay. Can I put a line through there that if I reflect over is going to get the same shape?
No.
No, I cannot. Now, up to this point, the only type of symmetry we've talked about is a reflection. There is another type of symmetry. Okay? It's what we call rotational symmetry. And what that says is that if I take this shape here and I spin it 360 degrees, so I take the whole thing and I spin it right around the middle point, so whatever that center point is, I spin it all the way around, how many times do I get this same looking shape? So how many times will it line back up with the original shape?
One.
Wait, two.
It's going to be twice, because I could take this and spin it 180 degrees, and it's going to end up right on top of it again. Then I can continue and go all the way back to the 360, which is a second time. So the way we say that is what we call twofold rotational symmetry. That twofold means that when I spin it 360 degrees, I hit that same shape 2 times. And we ignore the very first time, but we count when we come back for 360. So every shape is going to have one fold rotational symmetry, because if I spin it 360 degrees, I get the same shape. We're going to look at this more when we start to talk about other polygons, not just quadrilaterals, but other polygons. When we get to pentagons and hexagons and octagons and all of them. There's a nice type of symmetry that we can find there. But every parallelogram has twofold rotational symmetry. And that point that was in the middle that we're rotating around, that's that point, that intersection of the diagonals, that midpoint of my diagonals, where they actually cross each other. That's going to be the middle of my parallelogram. That's going to be what I'm spinning around. Pretty sure my notes go in a different order. So we might skip around to yours so that this matches up. All right, so let's go ahead and go to the next one. I have a proof next. So if you flip to the back side of that page, you have a proof?
No. Well, we have
You have a blank proof there. Does it say prove that opposite angles are congruent?
Yep.
Yes.
All right, that is what we are going to prove. Quite honestly, I don't care if you necessarily write this down as long as you are following the logic that I'm going through. Okay, so as long as you can follow along with what I'm doing, you don't need to write it down. But if you feel like it's going to be better for you to write it down, go ahead and do that. Okay, so what I want to do here is I'm given this parallelogram ABCD, and I'm told that it is a parallelogram. So that tells me that my opposite sides are parallel. So that's parallel, these are parallel to each other. I get all of that. Now I want to show that any parallelogram has opposite angles that are congruent. If I look in my proof that's already set up here, I'm going to pick one of my opposite angles. It's going to be DAB, it's my angle up here on the top left, and angle BCD. I'm going to show that just those two are going to be congruent to each other. So those two angles there. So I'm going to go ahead and write all of this proof in. What goes on my 0 line?
Given.
The given, so I'm just going to take my given, put it down there. Okay, what's my justification for there?
Given.
That's my given.
I like to give us stuff. That's nice.
Hmm?
It's nice that they give us stuff.
It's nice that they give us somewhere to start at least.
It's like Santa. Just
All right, let's look at our first line. We have AD is congruent to BC. If I look at my figure up here, that is this side and this side. And on that same line, I have that AB and DC are congruent. That is my top and the bottom. How do I know that those opposite sides are congruent?
Definition of a parallelogram.
It comes from that properties of parallelogram. We're going to say it's a property. It's not quite the definition. The definition is that they're parallel. But it's a property of a parallelogram. So it's a prop of a parallelogram. And where it looks like an 11, those are parallel. Okay, parallelogram. All right, now I have BD. That is my diagonal coming across the middle. I have BD is congruent to itself. What is my justification whenever I have anything that's congruent to itself? Asa?
reflexive property.
That's our reflexive property. Okay, if it's congruent to itself, it is reflexive. Reflexive. Now I have that two triangles are congruent. I'm looking at triangle ABD. That's the one on my top half here. This one up here. So ABD. Yes, I have a lightsaber for a pointer. That's great. Okay, and I have CDB, the one that's along the bottom here. How do I know that those two triangles are congruent? Sydney?
CPCF.
Not quite CPCF. That's going to get me to the next part. You're getting ahead of me. If I'm doing the triangles congruent to each other, I need to use one of my triangle congruence theorems. So that's side, 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 angle, side, angle, side, angle. Which one do I have here?
Side angle side.
Did I say anything about my angles yet?
No, side side side.
I just have side on one side here, and my side that's shared. Okay, so I do have side, side, side. So this is gonna be side, side, side. Now how do I go from a triangle to a piece? Sydney.
CPCF.
CPCF, congruent parts of congruent figures. Okay, so we've proved that in any parallelogram, okay, because we didn't use our picture too much, it helped us keep track of things. But for any parallelogram, those opposite angles are going to be congruent. Okay? Alright, I'm going to click forward just so these all type in, but I'm going to lose all my writing when I do it. So hold on one, and I will type in all these. Okay, so that is our finished proof there. Okay?
Yeah, please.
No, there are no proofs or quizzes, or proofs on your quiz or test.
Oh, for real?
For real, I love
Oh, great.
Okay. They're still good to know though.
That's okay.
Okay? They're not going away.
That's
They will come back again, but
Yeah, but it's
for right now.
It's not a set, so it's gonna be okay.
Alright, so we're looking at example 1 now, so if you flip to the back, hopefully example 1 matches what I have. I'm sorry, your notes don't line up. But we have a parallelogram WXYZ, and we have that WQ is 4, so let me go ahead and label that. So that is this side here is 4. I have that XQ is 6. That is that side there. So those are half of my diagonals. And then I have YZ is 7. That's my side here along the bottom. I want to know QY. What would QY be equal to? 4. Why is it 4?
Because
Bisector.
it is opposite of WQ.
Well, it's half of.
Well, half of.
So it's half of that diagonal, right? And we know that the other diagonal bisects the diagonal WY. And so if I have half of it already and that WQ was 4, the other half is also going to have to be 4. What about WX? My side at the top.
7.
It's going to be 7. What do I know about opposite sides in a parallelogram?
They're the same.
They have to be the same. So my WX is opposite of ZY, so those two have to be the same. So WX here is 7. Now we want to name both pairs of parallel sides. You can give me one pair, Asa.
WZ and XY.
WZ, that line, or that segment, is parallel to XY.
Would it be a line segment or a
I guess it would be a line segment. So ignore those arrows. Okay. What is my other pair? I have 2 pairs. WX and ZY. WX is parallel to ZY. Okay, this one here is an X. Right? All right. Now let's go ahead and look at example. So example 2, I'm given another quadrilateral. All I'm told here is that it's a quadrilateral, and I have that angle KEA. KEA is this angle here, this small angle, is 40 degrees. And I have angle EAK is 35 degrees. And that is all that I have. We can figure this out. Okay, I want to find angle EAW. What would angle EAW be? Hannah?
Wait, is it asking for like the whole thing or just that one part?
So I just want EAW, so that is this angle here.
Okay, that's 30.
Is this one 35?
Yes.
no?
Do I know that my angles are bisected?
No.
They are not.
40.
So we want to say that it's 40. Why do we want to say that it's 40?
Alternate interior angles.
Alternate interiors would imply that I have parallel lines. Did I say we had parallel
Is it because
lines?
you have 2 bisects?
I can
Alright.
I can get a protractor.
You could get a protractor. It actually turns out that we need to know that this is a parallelogram. Okay, so this is in fact a parallelogram. I'm going to tell you that. So now we can use alternate interior angles, which would say that this angle up here that is 40 is also the angle EAW, which is 40. What would that make the angle AEW? It's my other side over here.
35.
That's going to be 35. The other way we can see this, which is actually what we would need without saying it's a parallelogram, is that I have that rotational symmetry. So if I rotate it, this angle here, this angle here, that is 40, is going to rotate all the way around and end up back on top on this side. Okay? Same thing here, the 35 rotates around and is up on the side here. Okay? I do like having the lightsaber. It's cool. All right. It shows up better because my only other colors are blue and green, so it doesn't show up well on here.
Go for blue.
I kind of like
The blue's not going to
I
show up.
like the red.
All right, we're getting distracted. So I have EWA now. EWA is my angle at the top here. Let me get a new color. We'll do green. So this angle at the top, that does not show up. Let me try another one. Purple. There we go. So that entire angle at the top, what is that going to be?
105.
How did you get to 105?
The angle of A.
So 35 plus 40 gives you what?
75.
75.
180 minus.
And I can do 180 minus that. All of that comes from I have a triangle on top here. So if I get my pointer again, I have a triangle on top. I know these two angles are 35 and 40. I can add them together, subtract it from 180 to get my other angle. Okay? That other angle is then 105. Now I'm looking at angle EKA, is my angle down here. What is that angle going to be?
105.
That one's 105 as well. Same reasoning. I can make that triangle and subtract from 180. All right. Now I believe we're going back in your notes, okay, to the front side. Does it say sufficient conditions? Okay, that is where we're going. So we have a parallelogram. There's a lot of different properties that show up. We've defined a parallelogram as being a set of two parallel sides. If I have that, I know I have a parallelogram, I'm done. But what if I have just that the opposite angles are congruent? Does that mean that I have a parallelogram?
No.
It does, in fact. Okay? And so that's what we're going to look at here. We've defined it just one way, but there's several other things that we could have used to define it. Those are what we're going to call the sufficient conditions. So if I meet any of these conditions, that guarantees that I have a parallelogram. Sorry, my mind just went blank. So with all of these, it can be any one of these 5 conditions we're going to have. I don't need to have 2 of them. I don't need to have all of them. I just need one. And that's what all of the ors are for. So the first one is that both pairs of opposite sides are parallel. That is our definition of a parallelogram. Make sure you're still in your notes. And that is just our definition. We have that opposite sides are congruent. And I want to mark that on my picture here as well. So I can mark my opposite sides as being parallel. I will tell you as I advance forward through our notes, those lines are going to go away. So make sure you get those down. So mark that on the picture as well. I have opposite sides are parallel. Next we have that both pairs of sides are congruent. Okay, so both pairs of opposite sides are congruent. Okay, so I didn't say anything about parallel now, but I can still get a parallelogram if I know that my opposite sides are congruent. So I have opposite sides are congruent. Is that both pairs of opposite angles are congruent. This is the one we had just proved. So my opposite angles, those angles that are across from each other, are going to be congruent. So I have 2 pairs of congruent angles there that are across from each other. one pair of sides is both parallel and congruent. So I'm looking at the same sides that are both parallel and congruent. Alright, this one's a little bit harder to kind of comprehend and convince yourself that this one works, but it does. And the reason it does is because that distance between my parallel lines has to be the same. And if the segments of those parallel lines are the same, then I would have to go the same distance to connect them. So not only are those sides parallel, but they're also congruent to each other. So make sure you mark that as well.
Doesn't that apply to the other sides?
If it applies to the other sides, then I have one pair of parallel sides, and the opposite sides, those non-base sides, are congruent. What kind of figure would that be? If I have one pair of parallel sides and the other set of sides are congruent. Talked about it yesterday. It's not a rhombus. Not a kite. It's going to be a trapezoid. What kind of a trapezoid? Isosceles. Okay. I have parallel sides, and then the other sides are congruent. The reason that one doesn't work is I can take those sides and kind of fold them in, and so the distances on top are going to be different, top and bottom.
Isn't that is in between the sides and both supposed to be R? Or no?
It's is because it's one pair, so it's a singular pair. It's a weird. English is weird.
Yeah, I guess.
The other thing that we can have is going back to those diagonals, so the diagonals bisect each other. And that will also and if I draw on those diagonals, they bisect each other. Do they have to form a specific angle if they bisect each other?
Yes. No.
No. Okay, they don't have to be perpendicular. If they were perpendicular bisectors of each other, what kind of shape would it be?
Square.
Well, it would be a square. Well, it doesn't have to be a square. Not let me a rectangle. Not a kite.
Rhombus.
It's a rhombus.
Shape.
We said that with a rhombus, those diagonals bisect each other at perpendicular angles. Okay? Real quick, before I leave here, on our quadrilateral hierarchy, we said that a rhombus is always a parallelogram. That was that dotted line that we put in that we want to convince ourselves of later. These here, these sufficient conditions, are where we're going to convince ourselves of that. So let's start with the most basic thing about a rhombus. What's the definition of a rhombus?
All sides are congruent.
All sides are congruent. Look at the second one here. If all sides are congruent, do I have the pairs of opposite sides that are congruent?
Yes.
Yes. So would I have a parallelogram?
Yes.
Yes. So all rhombuses are parallel. Okay? Real quick. That's why that line is there. All right. Last example here. We just want to know, based on the information that I have, do I have a parallelogram? Okay? So I'm just going to quick draw a parallelogram just so that we can talk about the sides. So I have A, B, C, and D is my parallelogram. I want to know if the angle BAD, that's going to be my angle down here, is 60 degrees, and the measure of ADC is 60 degrees, this angle here. Would I have a parallelogram?
Yes. No.
We got to go back to those sufficient conditions. So what kind of angles would these be? Are they opposite each other, consecutive? What am I working with? What was that? They're consecutive. They're next to each other or adjacent. Okay. Do I have anything that says anything about consecutive or adjacent angles? I don't. What this is trying to get you with is to think that these are opposite angles. Okay. If they're opposite angles, then I'm partway there, but I actually need two pairs of angles to say that they're opposite, or that it's still a parallelogram. So this one does not work. That one's a no. All right, let's look at B. I'm going to draw another picture here. So I have A, B, C, and D. Okay, I have that AB is 11, BC is 15, CD is 11, and AD is 15. Would that form a parallelogram? You said yes, A, so why?
You have two pairs that are congruent.
I have two pairs that are congruent, and what are those pairs as far as their relationship to each other? They're parallel, but are they opposite each other or consecutive next to each other? They're opposite. That opposite piece is important because if I have two adjacent pairs, then I have a kite, and not all kites are parallelograms. Okay? All right, last one, I have that AB is parallel to CD, and AD is 8, BC is also 8. So I'm going to say BC is on the top, that's 8, AD is on the bottom, that is also 8. That's an 8 on the bottom, I promise. And then AB is parallel to CD.
Yes.
Sorry, this is A. Hold on. A is down here at the bottom. B, C, and D. Would that one be a parallelogram? So I have opposite sides are parallel. So I have one set of parallel lines, and then I have the other sides are congruent. Does that one fit one of my sufficient conditions? It doesn't. This is the one we were just talking about, actually, where it could be an isosceles trapezoid. Okay? Let me draw that quick for you. So if I have a set of parallel sides, I'm going to say now that this is A, B, C, and D. Those are parallel. Do we agree that that satisfied this first statement here?
Yes.
Okay? Now I'm going to say that AD is 8 and BC is 8.
That's true.
Now it's a trapezoid. Okay? So this one here is also a no. Okay, middle one was yes, top one was no. So I had no, yes, no there. Okay? Your homework is in the back board. It's also on your calendar for your notes. Okay? There are quite a few problems there, but they should be pretty quick. Okay, they're coming from 2 different sections. It's 7-8 and 7-7, both of those. Okay?